Hello everyone, welcome back to the Causality for AI and ML lecture, short CAI. Today we are just recapping briefly what we did in the sixth session, which was a coding tutorial on various topics and everything all that came before this sixth session. So we talked about discovery, identification, and so on and so forth. And during the live sessions, the students were actively engaging, and we were helping out here and there when necessary. So now it's just me post lecture recording a quick recap of the tutorial essentially. So what did the tutorial comprise? So it was a total of 5 exercises. We first did the Simpsons paradox, then we talked about parent adjustment, then backdoor adjustment, so ways of doing identification. Then we switched to actual machine learning and how to do estimation. And finally, briefly, we also covered a little bit of discovery. Again, as always, for all of these things, you could do a lot more exercises, but this is like a first dive into and giving, some intuition alongside a story to follow, which really fosters this intuition. Really, the idea was that of like supervised trial and error. So that's why we didn't record it live. But now I'm just going through it and showing you how to do it. Typically, we took like 5 minutes for each of these exercises to discuss the solutions and go over them. So that's really what we are going to do here. So we are not going to do 80 minutes now. It's just going to be quickly recapping what we learned in these exercises. So the first step is to go to the GitHub shown here on the slides. So you can find it in my repository. It's going to be the coding tutorial that we also used for the summer school this year, the European Summer School on AI. And you just need to go to the link and then just download the repository. And this is really just necessary because there's a couple of prerequisites, a couple of files and one little data set that we want to load into the tutorial eventually. So that's the only reason why we need this. Then you simply open the Jupyter notebook within that repository. So you can just click within the GitHub. Again, I'll show that in a second. And then you essentially just copy the link of this IPython or Jupyter notebook and go to the Colab site by Google, which is an environment to actually running this online. So you don't even have to use anything like IPython or Jupyter. So you can just do all of this online. We even have access to GPU, although, sorry, that is not necessary. Yeah, then you essentially just open Google Colab, click on the GitHub part, as you can see here, and add the notebook link. And then it's going to be shown, and then you can just click on it, and then actually the notebook opens. And now you're going to see the notebook where you can interact with it, just like you would if you had like a notebook offline. And then you simply just upload the remaining Python and table data CSV files from the local repository that we downloaded previously. And yeah, then it's really just coding, right? And sometimes you have to change something. Most of the times you actually just have to understand what's going on. So we are going to do that at least in a brief way. As always, if there's any questions, you can always reach us also after the lectures. Yeah, so let's jump right into this. So as you can see, we have opened now the repository. Here we're just going on this code part and going to download the zip archive. It's going to be done any second. Now it's downloaded. We can go back to our local file system and just unpack this. So here on Mac, I can just double click. Here it is. As you can see, here's the tutorial, but we are just going to use this, and this file. So now we can just go here and open the tutorial here to get the link. That's going to be this one up here. Now we go to the Colab. As you can see, we have reached Colab. We can click here on GitHub, add the link, enter, and then open the tutorial here. Nice. So now we're in this environment. As you can see, there should be something regarding the runtime settings. So here, for example, it's showing now with the GPU. That's fine. It's going to be just a little bit quicker. Here are the files. We're just waiting. Now we can upload. We click here on upload, go in here and just select the CSV and the two Python files and upload those. That's fine. Now we're good to go. So now we can just click here again and go through the tutorial. So again, big shout out to Alex, who was the main author for this tutorial. And we co-authored this together also with Philippe and Thibaut. Again, I said 5 exercises. Let's jump right into it. Notations and so on should be familiar, but we're going to cover those anyways. So here we have some utility functions that we're loading. That's fine. So you can see matplotlib, numpy, pandas, seaborn. So visualizations, data processing, stuff like that. And then we also have some discovery methods, which we're going to load and simply apply. For example, you can see here from linear is showing you the one from Notius, which is the one we uploaded with the Python file. And then here we just have some nice functions for, generating data, printing treatment effects, loading images and stuff like that. Nothing too crazy. So this worked out beautifully as well. As you can see, no errors or anything. Okay, and now we're here in the settings. So the story was the following. So the world is confronted with a rare disease for which the world's public health agencies are urgently trying to find therapies. And scientists have proposed a new drug, but its effectiveness has not been, fully demonstrated. So you are the government's top data scientist, and so you have been tasked now with finding evidence of the effectiveness of the drug. And obviously, this is not a light task, right? So also this tutorial was still developed when, the COVID pandemic was hitting strong, and so this is where the inspiration comes from. I think everyone can relate here. And yeah, so there's not enough time to run a clinical study. So we have to use, data collected in neighboring country who have already started giving drugs, right? And here we have simply the features that we're going to measure. It's going to be categorical, even binary in some cases. So we have the severity of symptoms, mild, strong, and critical, denoted by 0, 1, and 2, respectively. Treatment being given or not, dictated by either 0 or 1, and survival after a month of that patient. And yeah, good luck. So now the first thing we just do is load a data set. And that's the function we had earlier. And as you can see, we have different samples for Z, A, and Y with these values between 0 and 2 for Z and binary for A and Y. And now we are interested in measuring the average treatment effect, right? So the chances of survival, so Y being equal to 1, if someone has taken the drug or not, right? And so we might, be tempted to now first go with the following conditional quantity, where we have the expectation over Y in the group of people that had that were given the treatment and the group that didn't get it, right? So that's the difference here. So this we can just, here this function is just making sure that we plot it nicely, and then really you're just looking at the data points where A is equal to 1 and where it's 0, and then just take the mean of Y. Simple. So let's look at the plot. And so now this is typical part of the exercise. So you're looking at this, and now here's the question: what do you conclude? And you should not click on the answer before you have thought about it. So let's look at it. We can see that the value here is negative. So we would think that actually taking the treatment is kind of bad, right? So this is also visualized here by the plots. That given the treatment, the survival is expected around like 0.445 maybe, while it's closer to 0.6 for the one where we don't take, or where we look at the group that hasn't gotten the treatment. So that will be our answer. And now we look. It looks like the treatment has a detrimental effect on survival, just as we predicted, and that would suggest it's not effective. This is really odd. And you were told that this treatment is absolutely state of the art and it was likely to be effective. So you kind of question now whether this is the correct thing. And obviously, I mean, you have heard about all of these things in the past 5 lectures. We are in a causality lecture. This is not a causal quantity, it's a conditional one. So yeah, we got to explore this in more detail. So let us now look at the profile of patients that were treated. Are they special in any way, right? So what we are saying is we just want to plot now, the data distribution for the ones that got treatment, given the condition they're in, because we know there's different conditions: mild, strong, and critical. So let's do that. And as you can see now, this is far from uniform. So we see that most people who get the treatment are actually in a critical condition, whereas people with mild conditions usually don't get a treatment. And this, kind of makes sense, right? Because typically we just have so much medication that we can offer, right? And we would prioritize people who are in a bad condition. So the probability of being treated clearly increases with the strength of the symptoms. Exactly, this is what we have seen, and we have even justified it a little bit. This is probably due to some policy that the doctors were using to determine whether to treat patients or not. Exactly. I mean, the doctor, wants to ensure safety of the patients, and someone with mild conditions is more likely to survive generally than someone with critical condition. So far, so good. So let's look into the relationship between the strength of symptoms and the probability of survival. So we are just going to do the same scheme, just that we are going to look now not at A, but at Y equal to 1, so surviving patients. And now here we see the reverse picture, which really fits to our intuition that, people with mild conditions, they will recover themselves most likely, whereas people in critical condition really need their help. And in general, independent of whether they now, had gotten the treatment or not, because obviously most get it, but still not all. Otherwise, this value would be 1. You have still, people are less surviving. So let's look here. What do we observe? The probability of survival clearly decreases with the intensity of symptoms. Exactly. Now, let's look at this from a graphical perspective, shall we? So you decide to question the doctors on how they decide whether or not to treat patients, and they tell you the following. It's simple. We know that patients with strong symptoms are less likely to survive, so they will look at their symptoms and decide to treat whenever we anticipate a lower chance of survival. So if we now, recapture all of our insights so far and our thoughts, then, well, we have 3 variables, so there's going to be 3 nodes. And we know, obviously, that the treatment somehow has an effect on Y, so there must be an arrow going in that direction. But we also know now that the doctor is deciding based on the symptoms. So there's an edge from Z to A, which is really the doctor's decision, yeah? And now what we're also saying is that the severity of symptoms is obviously affecting, the chance of survival. So there's also naturally going to be an edge from Z to Y. And so we complete this triangle graph structure. So we have a fork on Z, and we have a little chain between A and Y. So this means that the difference in expectation that we measured can be due to any of the paths we saw before, right? So it can be due to A, causing Y, but it also can be because of this backdoor, right? Because there's some information flowing between A and Y via Z, right? Because that's the doctor's decision. Yeah. So said differently, essentially, also remembering, deseparation and so on and so forth. Essentially, if we know about that, if you know about the conditions, then, well, not in this case, because you would have this error here. They would not become fully independent, right? But if you knew about this, then at least you would correct for all of these things. And that's, well, I'm taking away a little bit already, but this is what we're going to see now with the identification step. Okay, so that's what we're going to do now. But first, in the gold standard way, which is randomization, right? The randomized control trial, or A/B testing. So let's assume now, hypothetically speaking, so we don't have this data, but that we could collect new data where we randomize the treatment, right? So we make it not dependent on the doctor. So essentially, we are going to ignore whether someone has mild or strong conditions and just give them the treatment, yes or no, right? So we're going to have 2 groups, and in those both groups, it's going to be mixed whether someone has, mild or strong conditions. It's not going to be biased towards the one with strong, yeah? And this in a graph means that the association now between A and Y must really just be due to this path, because again, Z has no connection whatsoever now again to A, because we randomized, right? So A is just being created on its own, right? Like whether someone gets the treatment or not. So that's what we are going to try to do now. So we're going to try to, randomize now this data set. And so we're going to use our function from before to generate data, but here we have to change a little bit, right? So that's why you see here that there's a spoiler, and we're clicking on this. So what do we see? We have to change the policy here, right? So the policy is the probability of treatment for each of the Z, right? So mild, strong, and critical condition, right? And what we're going to do is we are going to put them all to 0.5, right? So you're going to make this a uniform distribution. You might ask now, why is this not summing up to 1? Well, because we just have essentially these two states, right? And so either having either getting a treatment or not, and the probability of getting a treatment or not should be 50-50 coin flip in any of the states of condition that you can be in, right? So if we had multiple treatments, then this would be for example, say we had 3 treatments, right? Then it would be 1/3, because any of those treatment could be chosen at random from a certain condition, right? And then again, why are they all equal? So all of them are being put to 0.5 because none of the groups is going to be preferred in any way when it comes to that, right? So with this, we achieve true randomization. Everything else stays the same. So now we can just, rerun after having changed the code. And now here, I mean, you're not going to see much of a difference in the sense that you're just going to see again these numbers and they're going to be in the ranges again. But now if we look at the plots, obviously now this is going to change. So now as expected or as we intended, the propensity, so the probability of getting treated given our covariates, our condition, is now uniform across all of these conditions. So the strength of the simulants does not affect the treatment anymore. So now let's look at this quantity again now, right? So this conditional group. This will now correspond to the actual causal average treatment effect, which we typically denote by the do operator, right? Because we don't, the A group does not depend anymore on which symptom they have, right? Here, do operator, as we've seen before, here it would just mean that we are setting actively A to some value, and that would be called an intervention. And we can say that we had interventions now here by randomization, essentially. So we just decided 50-50 whether to put A to 1 or 0. So now what we can do is really look in the same way as before. We don't even have to change the code. That's the cool part. But given that the data is now different, we have now experimental data, essentially. We actually get the causal effect. And so now we're looking at the same plot from before, but this time around we have a flip in sign, and not just flip a sign, but also the strength of the relation is changing. So before we had something like minus 0.11, and now we have 0.27. So now we see, wait, the drug has a positive effect on survival. So people seem to be better off, with taking it, right? So if we compare now the numbers again, as we remembered correctly, so this one was negative, was suggesting it's actually detrimental to take the drug, but the actual causation is telling you should be giving the drug, and it actually has even a strong positive effect in comparison to what we anticipated before. So that's really it, right? And so our assessment before that was really just biased because of confounding, right? So if we just go back briefly and have the structure here, so Z is the confounder here. And, if we were not to observe Z, for instance, then, this would typically be called hidden confounder. Here, Z is observed, so it's not hidden, but it's still a confounder. And confounder really just means that the conditional and the causal effect really differ. Yeah? And they differed because of exactly this edge between Z and A. And there was this backdoor path, as we say. So yeah, this we have learned now, and this is really, the final words we are taking here. And, causal inference from observational data, that we can really just get it from the experimental ones, right? But, what if the experiments are unethical? So for example, say you want to have the effect of smoking on a disease in a patient, you're not going to make randomly people start smoking, especially considering that, there is the chance that actually it is a bad, right? And in this case, we know it is bad, right? And so for these reasons, you might not be even able to do experiments, right? So it's infeasible on many dimensions, and you want to do it with observational data. So there's no other way around it than, making assumptions. But if your assumptions are reasonable, then we can actually do causal inference. And so this is now exercise 2. So in exercise 2, we are starting with parent adjustment. So recall our graph. The graph could be decomposed as follows, right? So then we just have Z being exogenous, and then A depending simply on Z, and then Y depending both on A and Z. And now when we, force people to take the treatment, so actively setting A to 1 or to 0, then it was essentially like this hammer indicated. We are just, fixing the value and make it independent of its parents. And so in identification now, what we are trying to do is make assumptions such that we get this do quantity without actually having access to, observational data. Yeah. And so in parent adjustment, so I mean, you know this from the previous lectures, but really what we're doing is the following. So say, we want to have the causal effect of an intervention A prime on Y. We can rewrite it in terms of the graph structure like this. So we reintroduce the marginals Y, A and Z. Now replacing with the above definition that, setting A to some value is just going to be, this delta function on the A part, right? Because the probability of observing A prime to be A to be A prime in the setting where we set A to A prime is 1. And so, we replace the definition here. And then, we look at all the cases, obviously, where A is exactly this A prime. So it's going to be this formula. And now we just, get rid of some of the unnecessary slack. And ultimately, we end up with this adjustment formula, which is, in this case, the parent adjustment. So we are saying that if we consider the group Z and then just reweight by the probability of any Z without, the backdoor to A, then this quantity for that graph, if that graph is a true graph, will correspond to the causal effect, right? And that is what we call identification, right? So we are figuring out how to get rid of the do essentially in the left-hand side. So here you see there's no do anymore, and we're only using things that we know about, right? We measure Y, A, and Z. So now one of the famous quantities would be the ATE, the average treatment effect, and it's simply defined as this difference that we saw before, just on the interventional level, right? And so any of those quantities is really just defined as, an average over all the different Y's given the interventional distribution. So given that Y is just either 1 or 0, this term easily reduces just to this thing, right? Which is the parent adjustment. Yeah, so we get this thing, and then because above we know that this thing is this thing, and now we just have the structure here. So now this we can implement, right? We are not going to go over all of these codes, so I encourage you to go there. There's enough comments to understand this, but really we are just looking at all these things, right? So subpopulation of data where A is equal to A, and then just taking the Y mean again, and then this would be the expected one, and reweight it by, the probability, right? And just add it to the estimate, which works in this case because it's just binary, right? And then, yeah, we have our data here, and then we are going to use this parent adjustment estimator once where we have A1 and A0. So again, it's just going to be this estimator essentially, and then you have to have it twice, right, and take the difference. So let's run it. And now, as you can see, we get pretty much the same value, right? Obviously, there's some numerical differences. And this is just because we have finite data. In the limit, these would converge, right? We are not talking now about like how they would converge, how the error behaves, and so on and so forth. For the moment, it's just important to understand. Yes, so in randomization, we actually had experimental data and just looked at the groups. So we did the conditionals in an interventional setting and got the causal effect. And now we got the very same causal effect without actually doing any experiment whatsoever, right? So we just had the assumption of how the structure should look like. And we reasoned that this is reasonable, right? That, people would decide based on the symptoms and so on and so forth, right? So this is something, an expert could extract, right? And yeah, we get the true causal effect, right? And it's only differing from, running experiments in the sense that, the numbers, the numerics is playing out a little bit different, right? If you crank up the sample sizes in this notebook, you're going to see they're going to be a lot closer. Now, in our example, all the variables are discrete. So, we were able to estimate these groups by, just filtering the data and counting, right? But we could rely also on a model, right, which is trained to estimate this quantity by actual supervised learning, right? So this is known as Monte Carlo approximation, right? So we could just get this expected interventional value by an approximation. So say we just have n samples for some distribution, then the expectation of that quantity is simply the average of these values predicted by the model for in the limit. And so what you can do is simply say then, okay, this thing, right? We know it's this when we write it in terms of parental adjustment. Really, that is just an expectation here on the y path, which is then again just an expectation now also on the z part. So we have this iterated expectation. And well, on the z part, right, you just look at the different z groups and approximate it then here by this mean, yeah? And that's it really, right? And so this would be a way of going about the same thing with, yeah, essentially a model, right? So you would have this model, which just, this could be essentially like a regression, right? Or a classification. So a model which takes A and Z as input and predicts a given Y, right? And you take the average of your predictions for these samples, and then you get, in expectation, the same thing, which is different again from what we did here, where we're just counting in our data set essentially, right? And so not going to go over details here, but just going to show you, right, that, you can, we have this outcome model defined, right, which is just going to give you these conditionals. So it's nothing too crazy going on over here. It's really just, fitting the mean. We fit this thing, and then again, right, once for A1 and once for A0, and then print all the things. So let's run this. This goes quick. And as you can see, also with the Monte Carlo, here we are really matching the adjustment from before, right? Cool. So that was parent adjustment. Let's move on now to exercise 3. So in exercise 3, we are going to the so-called backdoor adjustment, right? So let's just remember for a brief moment, deseparation, Markovianity, faithfulness. So in Markovianity, we just have the assumption that deseparation statement on the graph is going to imply the conditional independence in the actual data distribution, right? And so if we have a fork like this, so C is forking on A and B, then yeah, if we just generate some data, and as you can see, so C is just some random variable, and then A is going to depend on C in just the same way as it's going to be. We collect all those together, and then we just plot different interesting statistics. So let's see. So what we are plotting here is now probability of B being 1 given A, and then also given A after we also additionally know that C is 0. And as you can see that when we know about C, suddenly these bars are almost the same, right? Really, in the limits, they would be the same because A and B become independent conditionally on C. Whereas if you don't observe C, then, B and A are not independent. So knowing that A is 1 increases your belief in B being 1, right? And so again, this is really what we have written down here. Now you can do the same drill also for, say, a chain structure, and doesn't matter in which direction the chain is going. So what you have now is here, A is the starting point, and C depends on A, and then B depends on C. Yeah. Other than that, it's the very same plots. And now you can see the same picture. This we know, right? So conditioning on C contains essentially all the information that B needs about A, right? Or vice versa. And so again, we have this uniformity or as soon as we know the middle condition. So same picture. Now it's going to be a little bit different. This we know from our theory. This is a so-called collider. So only after knowing about C, information can actually flow between A and B. So it's going to be the exact opposite essentially. And so let's see. Correct. So if we just know about A, they're essentially independent. But if we know about C suddenly, it informs our beliefs. So that's what we see here. Yeah. Also, we have the little cat emoji suggesting it's very strange. Yeah. Now, why do we look at this? Because it's very important now for the backdoor adjustment, since it uses the notion of deseparation to understand. So let's look in a more involved and interesting example. So we have the following graph now, where we have two confounders. So we have one called Z2, which is just like our Z from before. But now we also have the Z1, which is confounding the relation between A and Z2. So it's a confounder on a confounder, essentially. And more importantly, Z1 is not observed. That's why we have this dashed circle. The reason for this could be plenty, right? We are just saying that Z1 now requires an expensive measurement device. Say it's some biological process that, which costs so much money to measure, so you can just not measure it, right? Like you actually know it's there, but you cannot measure it, right? So the structure is like this, but you can never, collect data on that, right? So what can we do? Like, should we ask for the money to buy this expensive device and measure it? So let's explore now. So what we do now here is, just generate data according to this graph. And obviously you can go through this in more detail, but it's really not that important for the moment. So we are just going to take this data. What's just important to know is that it's really following the structure. So that's the truth for the moment. And now I'll just look at if A and the Z are independent. And so what we can see is now the propensity scores, they vary, both, looking just at Z1 and also at Z2. And so what do we conclude? Well, clearly the distribution changes, so there is a dependency between each of these variables. And this does correspond to our graphical intuition since they are actually connected via these edges, right? So yeah. Now let's look at the Zi and Y. Again, we are using the same techniques from the exercise before to plot. And again, we see varying bars across the different Zi when we know that A is 0. So what we're saying is that they are conditionally dependent given A 0, right? So that's also what we're saying here. Okay, and now looking at the graph, we see that our treatment A is connected to Y via the following paths. So there's A to Y, but then there's also these two backdoor paths, one via Z1 and 2, and then one directly via Z2. So the first one is the causal path, and this is the one we want to measure. Again, the others are backdoor paths. These we want to kind of block out, right, as we have done before. So notice how conditioning on Z2 should block all of the backdoor paths. This is now the interesting observation. If we go back up here just for a second, you're going to see that really the second path that we have goes through Z1, but then ends up again in Z2, right? So if we could somehow block Z2, that should also be enough to block Z1, right? This is what theory and the intuition is telling us, right? Because yeah, we get informed via Z1, but it always has to sink into Z2. That's the special thing about the structure. So let's check this also with our plots here. So that's what we're going to look at now. And what we can see now is that if we know that A is 0, and we also know that Z2 is 0, then varying Z1 will render Y independent of these others, right? So what do we conclude now? Well, changing the value of Z1 has no effect. So in other words, we observe that the probability of Y given A and the Zi's is just the same as given A and Z2 only. So Z1 and Y are independent given A and Z2. And this was expected again because all the paths always lead through Z2. So it seems that we don't have to worry about Z1. And given that Z1 was actually the one with the expensive measurement device, that's actually awesome, right? So let's now estimate the treatment effect. We are going to do the same drill. It's going to be a bit more lengthy and look more complicated, but really nothing crazy happening here. So again, what is the interventional distribution here? So let's reintroduce the marginals. So we are reintroducing A and the Zi. Then we are just reusing our derivation for the parent adjustment, right? So what are we doing? So we are just looking at Y given A and the Zi, and then the Zi, yeah, separately. So just that we have two of those now. Now we can, factorize the joint distribution. So what we can rewrite is this joint into a conditional and then this marginal. Now we use the knowledge that they are independent, right? So as soon as we know Z2, so yeah, what we get is then this quantity here. And now, so you just see that essentially Z1 gets dropped here, right? And then we know that, this thing is constant in the sum over Z1, right? So we can modify a little further even, right? And separate. And then since we know that if you look at all the different values, obviously this conditional probability can take is 1, we really end up with this formula. And this is now beautiful, isn't it? So what we have here is just saying the parent adjustment is totally valid, or the backdoor adjustment specifically, if we just go over the Z2 variable. And this was the whole deal, right? Like that we said, yeah, we know that the structure is like this, but we cannot measure Z1 because it's very difficult and expensive to measure. And now we see we don't even have to do it, and we can get the causality out here. So in Pearl's book and also some other literature that you have seen from the past lectures, this is really the backdoor criterion applied now on an example. So if we implement this thing here now, we're going to have a very, very similar setup as before. Yeah, so just going to run this. And now we are just going to evaluate with all these different approaches, the conditional, the backdoor, and so on and so forth, to have the great comparison, right, for this other data. And so what do we see now? Obviously, these are different values because it's a little bit different data set. But we can see that, you know, if we just take the conditional, obviously, because there's confounding, it's going to be wrong. If we just take the backdoor via Z1, so we actually measure this expensive device and then, you know, go via Z1, but forget about Z2, then again, we are wrong. And it's not going to be the same as just taking the conditional, obviously. But now if we do, you know, randomization, if that was possible, then everything is independent. The treatments are chosen independently. So we get a true causal effect. As you can see, it's overestimated by the conditional. At least, you know, the conditional is on the same sign. So in this case, if someone were to even act wrong, they might not do as much harm. But still, obviously, we can see that there's a significant difference in value. And then parent adjustment and backdoor via Z2, which is the important part now. Both of these approaches give us the correct causal estimate. Again, numerical values are varying just because, you know, of finite data. But really, this is the awesome part here, that we don't have to look at both Z1 and Z2, but just Z2 is sufficient to get the true causal effect, right? So yeah, this was exercise 3. Now, in exercise 4, we actually went for machine learning, right? Because now you're really a pro already at causal inference. So let's look at, you know, high dimensional data, such as, for example, images, right? Like you can have just, you know, I don't know, 10 by 10 pixels. That's a super tiny patch, and that would be already, you know, 100 dimensions essentially, which are measured then, you know, over 3 channels, maybe if it's colors, and then again, those can have value ranges of, say, 0 to 255. So yeah, quickly we get out of hand with these things. And so we want to look at this, right? And again, we are here in a AI and machine learning course, essentially, right? And that's what we care about as computer scientists, or in general as AI researchers. So what are we doing? We are now switching our mind to a completely different story, but still a very compelling and intuitive one. So you get a contract, right? So you are now a pro at causal inference, and you have your online advertisement that you know how to do treatment effect estimation. And so your customer now is a veterinarian, and they need help in assessing the effectiveness of a treatment. And by discussing with the customer, you understand that this is a simple case of ATE estimation with confounding, right? So you cannot just look at the conditionals, you need to consider the confounding. The nature of the confounding here comes from the fact that the data was collected by a human, which was likely to assign treatment based on anticipation of the outcome, just as in the previous exercise. So we have the same graph. That's easy enough. However, the customer now tells you that they lost the detailed information about the animals that were treated, right? So they just have pictures that were taken when they checked into the clinic, right? So veterinarian, right? Again, we have different animals, say dogs and cats. And we have now lost the information about the animals that were treated. Now you could ask, you know, how do we expect to use such data, right? So we just have take pictures of the ones that were checked in, right? So how can we know now, just based off the pictures, which animals, you know, were treated or not, right? Like, I mean, sure, there's maybe dogs and cats and whatnot, differentiating factors between, you know, the animals, which we could maybe extract from the images, but still, like, how should we know which ones get treatment, right? So can we deal with this data? And yeah, let's try this. Let's take up this challenge. So we could consider, of course, you know, neural networks to, you know, deal with the high dimensional, at least, you know, as a part of our estimator. And then what we can use is this technique of inverse probability weighting, right? Where this propensity score, so again, the probability of getting treated given your parameters, would be estimated using convolutional neural network, right? So we are really trying to figure out whether someone got treated based on the picture, right? And because it's a picture, we say, okay, we are also machine learning practitioners. Something like a CNN would be a good thing, right? So let's first now load the data set. So this data set is going to have essentially, the the yeah these three dimensions. So whether someone was treated, what the outcome is, and what the image is. But only, for a subset, we are going to be able to use this. So here we are just using Cypher 10 essentially. And what you can see, this is now the ground truth data set for the moment. So as you can see, there's some pictures of, dogs and cats in very low resolution. However, this is already complex, right? And then, whether they got the treatment, for example, this cat did, this dog also did, this cat did as well, and so on. But then, for example, this, whatever this is, maybe a cat did not get it, and then this, probably a dog, did also not get it, and so forth. And then, Y is just denoting whether, for example, they recovered or not, right? Given the treatment from whatever disease they had. And so now what we're going to try to do is estimate this propensity score, right? So with the data set we have here, we're going to try to figure out if we can, predict based on the image whether, someone gets treated or not, right? So again, remember the setting, yeah? So tells you that they lost detailed information about the animals that were treated, right? So essentially they don't know about the confounder, right? So they know that, certain animals got treated, right? But they don't know the detailed information about how they got treated, right? So what exactly about this certain patient was it that made the doctor decide that they get the treatment, right? So this information was lost. And now we just have the images, right? So we have now the task of figuring out, just based on the images, how the doctor decided to give the treatment or not for this particular setting, right? So this is the challenge. And again, we have treatments for these different patients. We just don't know what it was about those, right? And again, as we can see here, for example, the cat and the dog. I mean, it's cat and dog, but both got a treatment. And then we have examples of here, maybe a cat and dog who didn't get a treatment. So has it something to do with, it being cats or dogs? Has it something to do with maybe the type of cat or dog? Has it something to do with, something else? Maybe the color of the fur or whatever, right? So all of these things we don't know about now, but we are trying to use now machine learning to figure this out, right? And that's the super cool part. So what we are going to do now here is use PyTorch, right? And so we can also use CUDA if, you have the GPU running on Colab. And yeah, we're just splitting our data here in classic fashion, train and test set, train validation test set. So let's just load up the data first. Now we're going to define our model. We're going to really simple. We have these two convolutional layers. We have so fully connected ones. We're going to use ReLU activation functions, a little bit of pooling, and that's it. So also this is loaded. Now we just, our typical pipeline for, like evaluating on a test set, doing a training loop, right? So predicting, measuring a loss here. So here we can just use the cross entropy loss. We can use the standard Adam optimizer. And yeah, we're just going to train for 10 epochs for the moment, right? So let's just run it. It's going to take a moment, but still it's going to be really fast. So as you can see, the loss starts out with 0.7 almost. The accuracy is 0.5. And quickly already we are improving. So the loss on train and validation is both going down as it should, whereas the accuracy is improving. And let's see where we end up. So nice. So we're able to jump within the 10 epochs about like almost 20% points, both in train and validation. So we are happy with this. Now we just have this function that's going to give us propensity scores. So it's just going to be the softmax of the net outputs for, given Z and A. Yeah. So whatever you want to look at there. So let's define this function. And now we're just going to plot this, right? And we are going to use some kernel density estimation plots to get the propensity scores of the individuals in our data set grouped together. So let's see what happens here. This is going to take us a second, just like the training, but it's going to be quick as well. Cool. Now we have our plots and let's look at this. So this is a bit more complicated plot than the ones we have seen before. So let's look at how we interpret this. So what we are seeing on each of, so we have three plots, right? And these are empirical densities. Now, what are these densities? So let's focus maybe on the left-hand side first. So the blue one. So what we see here is on the x-axis, the probability of getting treated, right? So A being 1. So the probability of seeing any individual dog, cat, whatever animal to have received the treatment, right? And so any, vertical here would be, for example, the one where we have the peak here. This would be the amount of densities. That's what you see now on the y-axis, the frequency essentially. How often do we have the case that the probability of A being equal 1 is point, say, 6 here on this scale. Yeah. And then, for example, the second mode would be how often does it occur that the probability that someone received the treatment is 0.35, say, for instance. Yeah. So we can clearly see that there's two modes to our distribution over these probability values, right? So most often we find either that they have a bias of getting treated or not. And now what we're doing on the right-hand side is dissecting this. So we are looking at, because we know that some of these animals are cats and some of them are dogs, right? And so we have a hunch that maybe it could have something to do with this, right? So now if we look at the middle plot, we are conditioning now on the fact that we just look at cat images, right? So we know which ones are cats, and now look at the probability of it being being treated if it was a cat. And we can clearly see that it's corresponding to one of these um, means, to these modes, right? Whereas if we look at the dog, we have the other separation, right? So it seems that uh, the propensity indeed has something to do with whether the animal that we are looking at is a dog or a cat, right? Remember, we had these images of the patients, which are in this case dogs or cats, and we also had the information that whether dog or cat got treated, yeah, but we lost the information on what you know was the deciding factor that made it such that they got treated. Yeah, we just had the images, and now we learned a function which maps our images to whether they are going to get treated or not. Just a second. Now being predicted by whether it's a cat or a dog. This is the thing we discovered. So we have our model, which takes as input the image, and there's no notion of cat or dog itself in that, but now predicts, the propensity. And this we could do because we have the images paired, right? We have the labels. It's a supervised learning setting. And now it seems that by looking at this plot, what we have learned, or what our CNN has learned, is that if the image depicts a dog, then it's gonna get treated. Whereas if it's not a cat, where it's not a dog, when it's a cat, it's not going to get treated. Obviously, these are probabilities, so that's why we also had certain dogs, for example, which were not treated, whereas certain cats were treated. But this is really the plots that we are looking at here, right? So in summary, catness and dogness must have been the source of confounding here for whatever reason, right? Now we could do some kind of post justification and think about what was really the thing that what was maybe the disease or something that the veterinarian was looking at for it, to be something where only dogs should be treated, right? But think of maybe a medication which just simply works on dogs and doesn't work on cats, right? And that was really the source of confounding here. So now we can just do the ATE plots and everything just as before. Now just that we are going to use our neural net for the predictions, right? So here we are going to estimate y do A1 and here A0, again, take the difference, right? Just that we here now have our predictions by our model. So let's just run this. This takes a little bit more because obviously we are using the CNN under the hood to predict images, but still it's super quick. And as you can see, so if we had randomized the treatment, this would have been the true causal effect. So this is a gold standard. Again, typically you don't have access to this, but because we are here in a synthetic setting, we can actually have this number. And now if you add the conditional, again, it would be the worst case. It's not just, wrong in value, but also in sign. But our trained model is getting really close here, right? And again, it's a trained model, right? So the CNN is also not perfect in predicting, but to see that we are so close to the ground truth in this example already is pretty amazing. Okay, and now we're jumping to the final exercise, which is just, causal structure learning or causal discovery. Here we're just going to talk about two different algorithms. So one of them is fast causal inference. It's, this extension, which was shown to be complete for, these constraint-based causal discovery methods, a really classical method which uses conditional independence. Obviously, it assumes that, you have the perfect conditional independence tester, and that is hard, as we know from previous lectures. But, given that, and, given that you have faithfulness, so that you also have this equivalence between deseparation and the independent statements, we can really, use deseparation to reason about this and so on and so forth. And yeah. And then the second algorithm is no tiers, which is a more recent characterization in terms of continuous optimization of structure learning, not necessarily having to do anything with causality. It was used in causal context, and there's assumptions that can make it work. However, here it's really cool to see that, in general, this algorithm performs well, even though, it has issues with scaling, right? But then again, all of these algorithms, either it's a conditional independence test or it's the optimization procedure here, which make, learning DAX obviously difficult. And then obviously going for something like ADMGs is even worse. But yeah, let's not dive too deep into what is what, but just, understand what's going on here. So we are not going to implement these methods. Here, we're just going to load these different methods. So we just have this wrapper function, which chooses either of those methods and gives us the graph output. The graph will naturally be an adjacency matrix. Now we're going to load this data set from the CSV file that we uploaded separately. So here you can see it's continuous data, both positive and negative values. So we have the confounder, the gene B, and the phenotype. Here they're just marked because we know this is the ground truth structure. So we have a gene and we have a phenotype, and they don't causally influence each other. They are both being caused by this common cause, this confounder, right? So it's a triangle structure, but without a complete triangle, right? So it's just a fork from the confounder to the gene and the phenotype. Now, we can, predict using our models, the graphs. So as you can see, it was super quick. So we predicted now based on our data that we have above, both using FCI and OTS. And now what we are going to do is just visualize this whole thing, right? There's going to be an error coming up here. No worries. It's just because of, some dependencies issues with the visualization. So you're not going to see a graph structure, but what you're going to see is the adjacency matrix. But we know how to interpret an adjacency matrix as a graph structure, so we're just going to focus on this. So as you see here now, on the left-hand side, we have FCI, and on the right-hand side, we have no tiers. And FCI is predicting an undirected graph. It's just giving you the symmetric matrix, right? So it's saying that there's an edge from gene B to confounder, but also from the confounder to gene B. So really, it's just recognizing the structure, right? And the values here, for example, 2 are some special encodings for, what the edge type means, right? And you can look that up for the FCI, right? But yeah, it's really recognizing the correct structure, that there's no edge from gene to the phenotype or vice versa. But it just cannot decide now on the directionality. Of course, we know that it's the confounder to gene and confounder to phenotype and not the other way around. And this now is actually being discovered by Notius, which is cool. So you can see that there's an edge from the confounder to the gene B, as indicated by this 2.95, and then also from a confounder to the phenotype. And as you can see, it's also giving you a difference. So this is a linear estimate. So it's telling you that the coefficient for confounder on gene B is stronger than the phenotype, which is suggesting that the causal effect the confounder has on the gene B, that this one is stronger. And yeah, that's really it. That's the total summary for this. And yeah, we have seen different ways of, looking at causality, different perspectives, different aspects from lectures from before. As always, there's, plenty tutorials and references and so on, but we are going to discuss a lot more in the upcoming lectures as well. So yeah, please look out for this, and thank you so much. See you in the next session.